Dear children, we have discussed Gauss law. What is Gauss law? You know, that is the electric flux linking with a closed surface is 1 by epsilon 0 times the net charge present within the surface. That is mathematically, that is phi is equal to q by epsilon 0. So now we have to prove it. So prove the Gauss law. That means we have to derive the Gauss law by applying Coulomb's law. So here you take a point charge at O, a point charge Q at O. Let P be a point at a distance R from the point O. So you remember, to apply Gauss law, we have to imagine a surface. That surface is called as Gaussian surface. So what is Gaussian surface? So Gaussian surface, you remember, it is an imaginary surface which encloses the given charge, and the surface is such that the electric field at every point on the surface is same, and electric field and area vector are perpendicular to each other on the surface. So here you consider a point charge Q at O, P be a point at distance R from O. Let us imagine a Gaussian surface. That Gaussian surface you consider here in the form of a sphere, so that the charge is at its center. So you see, if you take a point P on the surface, Gaussian surface, what is the direction of the electric field due to this charge? That is radially outward. That is shown by this arrow mark. That is the direction of the electric field. And if you consider a small surface element, let it be ds. So now what is the direction of this area? Do you know? Direction of the area vector to this element is along the normal, so that is also radially outward. So now you see the angle between electric field and area vector. You know area vector is represented by n cap. N cap is the unit vector normal to the surface. So you see here electric field and area vector are parallel to each other. So if I will ask, what is the electric flux linking with this surface element ds? That equal to d phi is equal to E vector dot ds vector. So you know electric flux is the dot product of electric field vector and area vector. So now E ds cos theta, here theta is equal to 0 degree, so E ds cos 0 degree, that is cos 0 degree is 1, so it is E ds. Let it be equation number 1. So now I want to find what is the electric flux through the whole surface, through the whole Gaussian surface, through the whole imaginary sphere. So you say at every point, as every point is symmetrical to this point charge Q, so the electric field at every point is same in magnitude. That is, and what is its direction? That is radially outward. If you consider the point Q at here, so what is the direction of the area vector? That is also along the normal. So here also the angle between E vector and area vector is 0 degree. Similarly, here also the angle between electric field vector and area vector is 0 degree. So at every point on this Gaussian sphere or the imaginary sphere, the electric field has the same magnitude and the angle between electric field vector and area vector is 0 degree. So what is the net electric flux through this Gaussian surface? So phi is equal to E ds integration over the surface. It indicates that it is the closed surface. So you remember the Gauss law is only applicable to closed surface. So now as E is constant that can be taken out and ds integration that is S, as it is sphere it is 4 pi r square. So phi you got here E into 4 pi r square. It is your equation number 2. So you know according to Coulomb's law, electric field due to point charge E is equal to 1 by 4 pi epsilon 0 q by r square. It is the electric field at the point P due to this point charge. Not only at this point P, at every point of the sphere, the electric field due to this point charge Q is equal to 1 by 4 pi epsilon 0 q by r square. So from this equation 2, you got phi, in LHS you have phi, and here in the RHS E, in place of E you write this 1 by 4 pi epsilon 0 q by r square into 4 pi r square. So here you see 4 pi cancel, r square cancel, so pi is equal to q by epsilon 0. Let it be equation number 3. You see, it is your Gauss law. So here we derived Gauss law by applying Coulomb's law. Here question arises, Gauss law phi is equal to q by epsilon 0 if the medium is air or vacuum. If the medium is any other medium, then the formula will be phi is equal to q by epsilon 0 epsilon r, where epsilon r is the relative permittivity of the given medium. Or you can write q by epsilon 0 into k. K is the dielectric constant of the given medium. So here we derive Gauss law by applying Coulomb's law. Just reverse. Derive Coulomb's law from Gauss law. Derive Coulomb's law from Gauss law. Just reverse. This same thing, the procedure is similar as the previous one. Similarly, you have to take a point charge at O, you have to imagine a Gaussian surface in the form of a sphere, and you find the electric flux. You consider the surface element at P, you find electric flux through that element, then you find the whole electric flux through the whole surface. So that is phi is equal to E into 4 pi r square. So now you apply Gauss law. What is Gauss law? You know, according to Gauss law, phi is equal to q by epsilon 0. So now you compare equation 2 and equation 3. From equations 2 and 3, in LHS you have phi that equal to E into 4 pi r square in equation 2. In equation 3 also phi is equal to q by epsilon 0. So now you can compare equation 3 and equation 2, that is E into 4 pi r square is equal to q by epsilon 0, or E is equal to 1 by 4 pi epsilon 0 q by r square. Let it be equation number 4. So now it is the electric field at P due to this charge. So if you place a point charge Q0 or test charge Q0 at point P, then what is the force experienced by that charge Q0? That F is equal to Q0 into E. So this is equal to 1 by 4 pi epsilon 0 Q0 Q by E. In place of Q0 remains same. In place of E, you write this 1 by 4 pi epsilon 0 q by r square. So you got 1 by 4 pi epsilon 0 q0 q by r square. It is your, you see, it is your Coulomb's law. Hence, Coulomb's law is derived by applying Gauss law. So it is you are all about your Gauss law. So now applications of Gauss law. Applications of Gauss law. First one will find electric field due to uniformly charged infinite long wire. So the application of Gauss law is very important. You remember the first application. We have 3 applications in our syllabus. So the first application is electric field due to uniformly charged infinite long wire. So you see, it is a wire, infinite long wire. It extends minus infinity to plus infinity. It is infinite long wire. So now it is, let this wire be positively charged. Let P be a point at distance r from the wire. So here already told, to apply Gauss law we have to consider a Gaussian surface, that is imaginary surface. So here for our convenience we have to imagine Gaussian surface in the form of a cylinder. You see this dotted cylinder, that is the Gaussian surface. It is the Gaussian surface. So you see this cylinder has 3 surfaces. It is one flat surface, let it be S1. It is another flat surface, let it be S2. And this one is the curved surface, it is S3. So you see, it is the cylinder, it is one flat surface, it is other flat surface, and it is the curved surface. So you see, at this point for the flat surface S1, what is the direction of the electric field? As it is positive charge, it is towards right away from the charge, and area vector is perpendicular. So what is the angle between electric field and area vector? 90 degree. For this flat surface S2, electric field is away from the charge and it is area vector. What is the angle? 90. If you say what is the angle between electric field and area vector at here, it is electric field away from the charge, and what is the area vector? This one. And here also it is electric field and it is your direction of area vector. So what is your conclusion? The angle between electric field and area vector is 90 degree for the 2 flat surfaces S1 and S2. And for curved surface you see, it is the direction of the electric field and it is the direction of the area vector. What is the angle? That is 0 degree. If you consider a surface at here, surface element at here, as it is positive charge, electric field is away from the charge and area vector is along outward normal. Here you got the angle between electric field and area vector is 0 degree. So you got for flat surfaces the angle between electric field and area vector is 90 degree, and for curved surface the angle between electric field and area vector is 0 degree. So, and you consider, here you see the radius of the cylinder is r, and you consider the length of this imaginary cylinder, that is Gaussian surface, let it be L. So what is electric flux? That is the surface integral of electric field and area vector over the closed surface. So you can write E vector dot ds vector for S1, E vector dot ds vector for S2 plus E vector dot ds vector for S3. And you remember here I have marked closed side but not here because S1, this flat surface, is not closed itself. Similarly, S2 is not closed for itself. S3 is not closed for itself only. So when you combine S1, S2 and S3, then you can say it is that cylinder is the closed surface. So individually S1, S2 and S3 are not closed surface. That's why I have not marked closed mark on these surface integrals. So you remember just told for surfaces, flat surfaces S1 and S2, E vector is perpendicular to area vector. Therefore, for these two surfaces, the electric flux is 0. Therefore, from equation 1, you got phi is equal to E vector dot ds vector for S3 only. And you see, electric and area vector are parallel to each other for the curved surface. So this is equal to E ds cos 0 degree for S3, that equal to E ds for S3, and or phi is equal to E is uniform over the curved surface, so it is, so that can be taken outside of the integration, ds integration, that is E into S. What is curved surface area? It is the cylinder, so that is E into curved surface area is 2 pi RL. Let it be question number 2. So by surface integral we got the electric flux. Now you apply Gauss law because it is the application of Gauss law. Applying Gauss law, what is the electric flux linking with this cylinder? So for Gauss law, we have to see what is the charge enclosed within the cylinder. You see the length of the wire, charged wire enclosed by the cylinder is L. That is the length of the cylinder. Then what is the charge enclosed? Let it be Q. Then Gauss law, I is equal to Q by epsilon 0. That Q you can write as it is uniformly charged, and then you take lambda is the linear charge density because it is wire means the charge is distributed over the length. So Q is equal to lambda L, that is lambda L by epsilon 0. So by Gauss law you got phi is equal to lambda L by epsilon 0, and by integration method you got phi is equal to E into 2 pi RL. From equations 2 and 3, you got E into 2 pi RL is equal to lambda L by epsilon 0, or E is equal to lambda by 2 pi epsilon 0 R. It is the magnitude of the electric field at a distance R from a uniformly charged infinite long wire. So what is in the vector form? If you take it is the direction of the area vector, so electric field direction is along the direction of the area vector. Therefore, in vector form you can write E vector is equal to lambda by 2 by epsilon 0 R. You know, any vector quantity can be represented by magnitude into unit vector. Unit vector is your n cap. So E vector is equal to lambda by 2 pi epsilon 0 R into n cap. It is your vector form. So if you are asked to draw the graph between electric field versus R is the distance from the wire. Here E is equal to lambda by 2 pi epsilon 0 R. As E here you see inversely proportional to R. So the graph will be like this. So it is your electric field due to uniformly charged infinite long wire.